Okay, so let's just start. So we are 5 students now. In Moodle, we are 6 students, so maybe one is coming later, or maybe one registered wrongly. Okay, so my name is Holger Thies, and this lecture is Fundamentals of Communications Engineering. There's also a Japanese name of this class. It's called Tsushin Kogaku Tsuron. So this class is based on the curriculum of the Japanese class, but there's a class with this name this semester, and I think the content is quite different. So this class is mainly so today's class, our class is mainly about communication theory, and the Japanese one is mainly about computer networks, as far as I know. And there's one more thing. So I will record this class. So there will be lecture recordings that you can download in Teams. So that's in case that somebody comes late or somebody cannot make it for technical reasons or some other reasons, you can watch the lecture later. The recordings will be available in Teams after the lecture, but please don't share the recordings with other people. So they're just for you to use. Okay, so let's just start this lecture. So I will start with some basic information about this course. So as I already said, my name is Holger Thies. I'm assistant professor at Kyushu University at the computer science department since last semester. You can also reach me by email at thies@inf.kyushu.ac.jp if you have any questions. And since this is an online lecture, we also have a teaching assistant whose name is Tanya Sultana. So she is here to help you if there are any technical difficulties. So if you cannot log in or if there's something, you can ask in Moodle and she will help you. Time and place of this lecture is, well, the lecture is online because of the coronavirus, and the time is always from Wednesday in the third period, that is from 1 o'clock to 2:30. And if you made it to this class, then you already know that there's Moodle available. So on Moodle there's the link to Teams, so you already should be registered on Moodle and should be able to attend if you're able to attend. And I'm also trying to always upload the slides on Moodle before the class starts. I'm not sure if I can always make it because I'm still working on the slides, but usually I will try to upload it a few days in advance. And yes. So that's about Moodle. And one important thing is about, so one more thing, so class, it's a little bit difficult. It's kind of a little bit a difficult situation. So I would kind of like it to sometimes ask a few questions and have somebody respond. But I will try that a few times in the lecture and see if somebody responds, and if not, then I will just give up. So, but let's try. And about grading of this class, well, so this is probably what you're interested in most. So grading is there is 20% of grading, around 20% of grading will be due to attendance. Then there will be maybe 1 or 2 exercises. So the exercises will mostly be not so. So it will just be something like a quiz on Moodle or something where you can fill it on Moodle, and it will just be some multiple choice questions. And in the end, so I'm planning to have an exam in the last lecture, which will also be a quiz on which will also be using Moodle's quiz functionality. So the last lecture will be for the exam. And there's one more point. So you should try to attend most of the classes, because it counts for your grade. And also if you attend less than 30%, that is, if you're attending less than 5 classes, this leads to automatic disqualification. So I want you to attend at least 5 classes to be able to get a grade for this lecture. If there are some, so this is if if you're not here without a reason. So if you have some very good reason to not appear, so please contact me in advance. You can write me by email or on Moodle, and then we will try to figure it out. So references for this class. So first, you don't need any textbook for this class. The class will be self-contained. But if you are interested in this topic and want to learn a little bit more, so those are the 3 main references I use to make this class. So the first one is by Carlson and Crilly, called Communication Systems. The second one is by Lati, called Modern Digital and Analog Communication Systems. And the third one is called Introduction to Analog and Digital Communications by Heiken and Mohr. Okay, so that's everything about organization. Are there any questions so far?
No.
No questions. Okay, thank you. Then I will just start with the lecture. So let's see what we will do in the whole class. So this is the syllabus for this Fundamentals of Communication Engineering class. So the first lecture, today's lecture, will be an introduction and overview over the class. Then the second lecture will introduce you to what signals and systems are. Then we will have probably 2 lectures on Fourier series and Fourier transform. So give you the backgrounds that we will need for the rest of the lecture. Then we will have a lecture or 2 about analog modulation, 1 about digital modulation. And then we want to talk a little bit about noise in such systems. So we need a little bit probability theory. So there will be 1 lecture which will just be a repetition or just be a basic introduction to probability theory. And then there will be 2 lectures about noise, 1 in analog systems, 1 in digital systems. And then the rest of the class will be about the topic of computer networks. So that will be 3 or 4 lectures in the end will be about computer networks. And then I will also give a brief recap in the end, in the second to last lecture, because the last lecture will be for the exam. So in total there will be 15 lectures, and we will have the content covered in the first 14 lectures, and the last lecture will be for the exam. Okay, so then I will start with today's lecture. So what will I talk about today? So today's lecture will just give you an overview over the whole class in simple terms. So the goal of this class is that you know all the topics, that you have an idea of what all the topics I just showed you on the previous slide are about. So just give a brief introduction about each topic and what it is about. So the main topics are what is communication, then introducing the elements of a communication system, then analog and digital systems, then talk a little bit about noise modulation, redundancy and coding, then about media, and a little bit about computer networks. And in the end, if there's time, I will talk a little bit about the history of the history of communication. So let's start with the fundamental question of this lecture. So what is communication? So Shannon, in his very important paper, in his fundamental paper of 1948, which is the start of modern communication and information theory, defined communication as the fundamental problem of communication is that of reproducing at one point either exactly or approximately a message selected at another point. So in simple terms, this just means the communication system has the goal to transfer a message from a source to a destination at some distance away. So this is a very general definition of what a communication system is. So let's look at some examples of which this definition could fit. So some simple examples that you all should know. Well, a radio is, for example, a communication system which transfers voice from the source, which transforms voice messages from the source to the destination. Then we have a TV which transforms sound and picture. Telephone also transfers voice. Then of course a cell phone. Then we have maybe you have seen a walkie-talkie before. So a walkie-talkie is similar to a cell phone. Well, similar to a phone, but it's The difference is that you always have to press, so only one person can talk at a time. So you have to press the button to talk, and if you don't press the button, you cannot talk, and only one person can talk at a time. And another example is the communication satellite. And of course, a big example is also computer networks, and there can be many different types of computer networks, but they are all communication systems. And we can give a little bit more we can classify communication systems a little bit more. So one possible classification of communication systems is to separate them into broadcasting and point-to-point systems. So a broadcasting system is a system which has a single broadcaster, like a big antenna, and multiple receivers. So basic examples are, for example, radio and television. So those are basic examples for broadcasting systems. And the other type of communication system is a point-to-point system, which has a single transmitter and a receiver. So if an example is a telephone or some types of computer networks. And there's another form of classification which is somehow a little bit similar. So that's the classification into simplex and duplex. So a simplex system is one that has only one directional communication. So that has one sender that sends to one or multiple recipients, but the person who receives the message cannot answer. So most broadcasting systems like radio and television are in this way. And there's duplex systems which allow bidirectional communication. So that means you have communication in both directions. So you can send a message, and then the receiver can also send a message to the one who sent the message. So and there's a further classification of duplex systems. So you can classify them into full duplex systems, like a telephone, where both people can speak at the same time. So where you have bidirectional communication at the same time, and half duplex, which actually is just always single direction communication, but you have two channels. You have only one channel, but you can use it in both directions. So in a walkie-talkie, you have to press the button, and then you can speak in one direction, and then the person who answers has to press his button, and he can speak in one direction, but you can never talk at the same time. Okay, let's see how a communication. So let's see what all those different communication systems have in common. So what we want to do in communication theory is we want to find a generalized mathematical model of all these different communication systems. So we have to find out what they all have in common. And this following block diagram was proposed by Shannon in his fundamental work about communication theory. So the idea is that every communication system can be every communication system is kind of built of these blocks. So you first start with some input message, and the goal of the system is you get the input message and you produce some output message at the you get this input message at the source and you produce an output message at the destination, and you want to produce an output message that is as close as possible to the input message. And what exactly the input message is, it depends, of course, on the context. For example, it can be a sequence of letters, it can be a sequence of words, it can be a voice, or it can be a picture, or many more. So usually this message is non-electrical. So communication systems always send electromagnetic waves through some channel. So the first thing we have to do is, because the message is non-electrical, it has to be transformed in an electric waveform. So this is what the input transducer. So this is what the input transducer does. So it takes the input message, which can be many different things, and converts it to an input signal. And so examples for input transducers are, for example, microphones, which a microphone takes a voice message. A microphone takes voice and transforms it to an electromagnetic wave. Another example is a computer mouse or a keyboard that transforms the movements of your hand to a wave. Okay, and so after the input transducer, we have the input. So what we have now is the input signal, which is an electromagnetic wave, and but this signal might not be in the right form yet. So it might be necessary to encode this message. It might be necessary to do some encoding. It might be necessary to change it a little bit so it can be transmitted. And this is what the transmitter does. So it processes the signal to make it suitable for the channel. And then we have the transmitted channel, the transmitted signal, which will be sent over the channel. So the channel is the physical medium that is used to transfer the signal from the source to its destination. So examples for channels are, so for example, wire, optical fiber, or also wireless interfaces. So the channel is the physical device that is used to bring the message, bring the signal from the source to the destination. However, the channel usually cannot transfer the signal perfectly because there's some distortion and noise in the channel, because it's a physical medium. So we have some distortion and noise, which leads to changes in the signal, and this is why the received signal can be slightly different from the transmitted signal. So then we give this received signal to the receiver, and the receiver has the goal to reconstruct the original signal. So it has to undo the changes made by the transmitter and the changes that have been made to the signal during transmission. And finally, there's the output transducer, which transforms back from an electric signal to the original message. So examples for output transducers are, for example, speakers or a TV, which gives you back the image, or a PC monitor. And in this lecture, we only focus on the inner part of this diagram. So we assume that we already are given some input signals. So we are just interested of getting an electromagnetic signal, an input signal, to an output signal at some other point. And we do not care for what kind of information. If for example, the signal contains voice or video or any kind of other information, we do not care about that. We just care about accurately transforming an electrical signal through the channel and reproduce it at the output. Okay. Any questions so far? If not, I will go on. And this lecture is called Communication Engineering. So of course, in communication theory, we can also look at different kinds of communication. We can look at communication, just communicating between people with voice, or communicating with, for example, something like drums. This all falls under communication. But in communication engineering, we are thinking about electrical communication, so telecommunication using electrical devices. So in our case, the input message is always transformed into electromagnetic energy, and signals are transmitted in the form of voltage or current through wires, radio emissions through the air, or as light through optical fibers. So we always regard signals as electromagnetic waves, and we will see in the lecture about Fourier transform that all the signals, at least all the signals we are interested in the physical world, can be decomposed in so-called sinusoidal waves. So sinusoidal waves are waves of this form, A times cosine omega t plus phi. So they look somehow like this, and they can be classified, for example, by their frequency. So frequency of a wave is so those waves are periodic. So that means that they repeat after a certain amount of time, and the frequency is just 1 divided through the period. And there's another important classification of such waves, which is the wavelength. The wavelength is just the speed of light divided by the frequency. And since we can decompose all signals we are interested in such periodic waves, we can always talk about frequency of a signal or wavelengths of a signal. So those are physical entities of our signal. And so what are electromagnetic waves even? So for electromagnetic waves, it's important to know a little bit about the electromagnetic spectrum to know what kind of waves there are. So the electromagnetic spectrum is the range of frequencies of electromagnetic radiations. They are differentiated by wavelengths, or as we have just seen, equivalently, they can be differentiated by their frequency. The longest waves are the waves below here. They are called radio waves. They have wavelengths from around 1 meter to up to 1 kilometer. And they are used extensively in communication. For example, well, they are called radio waves, so they're used for radio and also for TV and so on. There's also, we call radio waves with a wavelength longer than 10 meters, sometimes long waves, and shorter ones we call medium or short waves. So those are radio waves, and above radio waves we have microwaves. Microwaves are, for example, used in cell phones, radars, microwave ovens, and in communication satellites. Then with even larger wavelengths, so it goes from highest wavelengths to shortest wavelengths. So with even shorter wavelengths and higher frequencies, we have infrared waves. So infrared waves, for example, there are thermal infrared waves, which are emitted by the sun, fire, and other heat sources. And for higher frequency infrared is used, for example, in remote controls. Above that, from wavelengths from 700 to 400 nanometers, we have the visible band, which is just a very narrow slice in the electromagnetic spectrum. And in this visible band are just all the colors we can see with our eyes. So they go from red to the which has the highest wavelength to violet, which has the shortest wavelengths. And then, as the name suggests, there come ultraviolet waves, which are not visible anymore, but they are, for example, they are responsible for producing vitamin D in the skin, and they have also applications in sterilizing products. And then we have X-rays, which have wavelengths from in the nanometer scale, so from 1 to 10 nanometers. They can pass through tissue like the skin, but not through dense materials like bones. So that's why they are used in, for example, in medical tests and in security applications, such as scanning luggage at the airport. And then we have even shorter gamma rays. They have some so they are radioactive, and they have some they have some applications in medicine, like killing cancer cells. In communication, the waves we are interested in are mostly mostly have frequencies below microwave level, so wavelengths of 1 centimeter up to maybe 100 meters. The longer ones are not so interesting also for us in communication, and so those are the ones we are interested in this class, because they are used in communication systems. Okay, so there's one more thing about communication systems. So what we have seen, so we want to transfer some signal through a channel, but there will always be some distortion, interference, and noise. So there will always be some noise that changes the signal. So, and we can classify those unwanted effects during signal transmission into different types. So one is distortion. That means perturbation of the signal because the system, for example, the wire, is not responding perfectly to the system. So we can maybe we send out some signal, and then there will be some time delay until the wire responds, or until the system responds, and this is called distortion. Then there's interference, which is contamination by other signals such as power lines and so on. And there's noise, which is random electrical signals produced by natural processes. And we will always have those problems in communication, so we can never assume that we can transfer the signal without any errors. And then another important classification is distinguishing between analog and digital communication. So analog communication means we have continuous values. So values can take any. That values can be continuous. So that means they can take any point on the any real value on the x-axis. So there's no distance between single points of a line like this. That means that those are continuous values. And in contrast to that, we have digital signals. So digital signals means there's only a finite set of possible values. So for example, the most common one is digital signals. So in digitals is binary signals. In binary signals, we only allow zeros or ones. So the message, the signal can only take the value 0 or it can be 1, but it can take no value in between 0 and 1 and no other value. And of course, well, it doesn't have to be binary. It can be any other encoding. But the thing is that there has to be a finite set of possible values. So let's look at some examples. So analog systems are those that occur in nature. So for example, human speech is an analog signal, and other forms of sound are an analog signal. Light is an analog signal, and also temperature. So all those they do not take discrete values, but they can take any value. So temperature can be 35.5 degree, 35 degree, or any value in between. And the same is for the intensity of light or sound or human speech. Digital signals are, for example, text, which can only have which only takes values from a set of letters or from a set of words. It can be binary codes. Computer files are digital signals, and things like Morse code, which is also an encoding which is also a finite encoding. And there are several advantages. So usually we prefer using digital communication because there are many advantages of digital communication. So let me list some of the advantages. So one is privacy, because digital data can be easily encrypted. There's also multiplexing, which means that we can send more than one signal and can merge it together to a new signal. So we can merge two binary messages, encode it, and have one binary message that encodes both messages. So this is called multiplexing, which means different data can be merged. Also, coding can be used. So coding can be used to send some additional information that can be used for error correction. So it can be used to detect and correct errors. It's also more robust, which we will also see on the next slide. So robustness means that digital data is less sensitive to noise and other disturbances. So if we change digital data a little bit, if we don't change it too much, then we can always recover the original digital data, which is not true for analog data. And one more example is that digital data can easily be saved, for example, on hard disks in a computer and so on. Okay, let's look a little bit deeper into one point. So I just said that digital signals are more robust to noise. Why is that? So, well, this is quite easy to see. So if we look at a digital signal like this, so a digital signal only takes value. So for example, this is a binary encoding, so it can only take two different values. So it takes values of minus the amplitude or plus the amplitude, and there's always some large distance between one value and the other one. So what then happens? there will be some there will be some distortion first. So if we try to send this digital signal through the channel, there will be first some distortion. So there will be some delay in sending. When we send the signal, the channel will not respond perfectly. But when we go from -1 to 1, or from minus the amplitude to plus the amplitude, it will take some time for the channel respond. And if we go back, it will also take some time. So we will get a waveform like this. And then there will be some noise and interference. So even this signal will have some slight bumps and so on. It will change a little bit. But if the change is not too much, since we know that the values will always be between -1 and 1, we can reconstruct the signal easily. So we can look at how high do we go, and then if we are higher than a certain amount, then we just say this is 1, and then if not, we just say the signal, the bit we send is or the code we send is -1, and then we can easily reconstruct this digital signal if the change is not too much. And this is also this point that the change cannot be too much is also important, because we can even if there's lots of change through if we go very far, if the distance is very long, there might be a large change. But since if the distance is shorter, there will be only little change. So we can reconstruct the signal at some short distance and use repeaters to send the signal again. So repeaters means we get in the changed signal, then reconstruct the digital signal, and then send it out again. So we will always have only little change between repeaters, and in the end we will be able to reconstruct the signal well. This can of course not be done for analog systems, because analog systems, the values can be anything. So even after a short distance, we cannot reconstruct the signal perfectly, and we'll always have some error. So if we send an analog signal over a very long distance and there's lots of interference and so on, then it will be very difficult to reconstruct the signal perfectly. But one important thing to remember is that digital signal, so there's actually digital signals actually do not really exist in the physical world. So if we send a signal through a channel, it will always be analog. It will always be an electromagnetic wave, which is analog. So we cannot really send a digital signal, and all the signals we have in nature, like voice and so on, they will always be analog systems. They will always be analog signals. So an important thing what we can do is we want to change an analog signal to a digital signal that we can use to recover the original analog system. So this is what is called analog to digital, or AD conversion, and that means we are given some analog signal like this, and we want to get a close digital approximation to the system. So this is usually done in 2 steps. The first one is called sampling. So sampling means we pick some discrete time values with equal distance, and then take the value. So we only take the value. We measure the value of this analog signal at those time points. So, for example, in this case we take some samples at those points here that are marked with the red arrow, and then write down the values that we have, and then we get some finite approximation of the system. But this is still not. Then we get some finite approximation of the signal, but this is still not a digital signal, because it can still. Well, if we just sample at some points, we will still get some continuous values. So the values can still be any real value. So the next step we have to do is called quantization. So quantization is kind of similar, but now we now we take the axis of values, the axis for the values, and split them into discrete splices like this. So we kind of round the values to so we have some splices like this, and then round the values to lie inside of one of those slices. So, for example, in this case, we would round those values and then get a digital signal, which looks like this. So this would be a digital approximation of this function. And an important question is, let me go back one. So an important question is, how good should we do this? How good should we do the sampling? How many points should we take to get back a good approximation? What is even a good approximation of this signal? So if we look at a signal like this, so as I told you, every signal can be decomposed into waveforms like this. So it will be some periodic wave like this. And let's say we just take very few points. So we take just maybe 3 sample points, and then somebody tells you, please reconstruct the wave you get from this signal, from the wave you get the waveform you will get from those 3 points. But you cannot do that because it's too many. It's not enough points. But if we take much more points, then you will get a very good. And you have a waveform, then you will get a very good approximation. So you can think of if you just get those points, you will probably be able to reconstruct the original signal. So the question is, how many points are enough? So of course we cannot take infinitely many. We cannot sample at infinitely many points, only at finitely many. So we have to know when it is enough. And this question is answered by the famous Nyquist sampling theorem. So for this, we look at the frequency of the function. So what I told you on the previous slide is, so periodic signals always have a time period. So they repeat after a certain amount of time, and the frequency is one divided by this time period. And what Nyquist sampling theorem says is, if the signal does not contain any frequencies higher than the frequency fm, so the frequencies of the signal are bounded by some frequency fm, then it is completely determined by uniform samples with distance larger than 1 to fm. So that means if we use as a sampling frequency more than double of the message frequency, we can reconstruct the signal perfectly. So if we take points at distance a little bit any less than half of this time period, then we can reconstruct the signal perfectly. Okay, any questions so far? If not, let me go on. Okay, one more thing I want to talk about today is the fundamental limitations of communication systems. So one thing we always should remember is that physical systems always have noise, because so we cannot construct a physical system. We cannot construct a physical system that doesn't have noise, because there will even be at the atomic level, there will be some noise. So it's impossible to physically construct a system that has no noise. So, and because there's always noise, there will be some fundamental limitations. To understand these limitations, we can look at the following quantities of a communication system. So we can classify a communication system in by those 3 things. So the first one is the channel bandwidth, which is the range of frequencies the channel can transmit. So there can be a limit on the highest and lowest frequency that can be transmitted through the channel, and the bandwidth is the range so it's the highest frequency minus the lowest frequency. So the range of frequencies that can be transmitted. Then there's some, so there's some electrical power. So the signal will have some electrical power, and the signal power is the average power of this transmitted signal. And there's the signal to noise ratio, which means the signal power divided by the power. So we can measure both the signal power and the power of the noise in volts, for example, or because those are electrical signals. And then the signal to noise ratio is the ratio of the signal power to the noise. So signal power divided by noise. And well, of course, some limitations are that the first limitation is that the bandwidth of the channel, always has to be large enough so that we can transfer the signal we want. So, for example, signals have also a certain bandwidth. So, if we want to be able to hear voice, so human voice in an understandable way, then there are frequencies between. So, human voice has frequencies from around, I think, 300, maybe 300 hertz to around a little bit more than 3000 hertz. So the bandwidth of human voice will be around 3000 hertz. And there's the other example is image signals. So television signals usually have a bandwidth of 6 to 8 megahertz. So this is the first limitation. So if the channel bandwidth already is not large enough for the signal, it's already lower than the signal bandwidth, then of course we cannot transfer the signal perfectly. There will always be something lost. Then there's another thing we can look at. So this is the rate of information transmission. So that means, the rate of information transmission is usually measured in so a measure of rate of information transmission is the maximum number of binary signals, of binary symbols that can be transmitted per second. So the unit for rate of information is bits per second. So how many bits can we transfer per second, which is the rate of information, and it's kind of so we can see that this rate of information transmission should always be proportional to the bandwidth of the channel. So why is that? So the idea behind this is if we have some if we have some some periodic signal of a certain bandwidth. So bandwidth is kind of how often does the signal change. So how many, so if we look at a signal like this, so the frequency is how often, so a higher frequency means that the signal changes more often. So that means if we increase the bandwidth, so if we allow more frequencies, then we can encode more, then we can compress this. We can make this wave smaller, which means it has more bulbs like this. So it changes. Higher frequency means it changes more often. So we can, if we allow higher frequency, we can compress signals and get more information through the channel. So that means this is why the rate of information transmission is always directly proportional to the channel bandwidth. On the other hand, there's also a relation between the signal to noise ratio. So the signal to noise ratio, so the intuition behind that is that if the signal is much stronger than the noise, then we have more steps. So we can encode the message in steps of the noise, because if the signal is weaker than one step of the noise, then we cannot distinguish between two values. But if we have more multiples of the voice, more multiples of the noise available, then so if we have a higher signal to noise ratio, then we can, for example, instead of binary encoding, encode 5 or 6 bits with just using different power levels. So we can use 1, 2, 3, 4, and 5 times the noise if the signal to noise ratio is, for example, 6. And so this is the idea behind Shannon's equation. So Shannon's equation gives a theoretical upper bound on how much information can be transmitted through the channel. So we cannot. So in this class, a proof of Shannon's equation is beyond the scope of this class. But what I just said about that we can. So that the channel bandwidth is proportional to the information transmission, and that we can encode more information if we have more power, is kind of the idea behind why this equation holds. So the equation says that the maximum information that can be transmitted is the channel bandwidth times the logarithm of the 2 logarithm of 1 plus the signal to noise ratio. So it gives a mathematical upper bound to the information that can be transmitted. So one thing about this equation, this is of course, so noise can have many different forms. And although we will not go into details yet about this equation is only true for a certain type of noise, which is called additive Gaussian white noise, which means that the noise is added to the signal and is equally distributed over all frequencies. So if we have this kind of noise, which is a quite good model for noise in most communication system, then this Shannon's equation will hold. And of course, now what one could say, well, if we increase bandwidth, we would always get. If we increase bandwidth, we would always be able to transfer more. We would always be able to transfer information much faster. So why don't we make the bandwidth as large as possible? But in practice, this is often not possible because bandwidth and noise are often connected. So increasing the bandwidth of a channel will usually also increase the noise, because the noise is, so the idea behind this is that the noise is, that the noise is at all frequencies we have some amount of noise. So if we allow more frequencies, then we will also have more noise. So it's usually not possible to make the bandwidth indefinitely large. So those are so this is why those are some fundamental limitations of the communication system. Okay, so let's look at some examples. So again, recall that so I have Shannon's equation here. So Shannon's equation again says that the capacity of the channel is b times logarithm 2 of 1 plus the signal to noise ratio. So let's look at some examples. So if the noise is much larger than the power, so if the signal to noise ratio goes to -infinity, then nearly no information can be. If the signal to noise ratio goes to gets very large, gets very small, then no information can be transmitted at all, because then this goes to 0. And if there's no noise at all, so if the signal to noise ratio is infinite, then theoretically any amount of information can be sent within 1 second. So this kind of makes sense, because if there's no noise, that means we can measure the signal we send. We can measure the power we can measure the power perfectly. We can measure the power of the signal we receive at the end perfectly. There will be no change in the signal strength. So we can measure the power, and we will have any value. So we can make indefinitely small. So we can make we can encode indefinite. We can encode any message. For example, in GEL, we can give any message to one very small slice of power, and then we will be able to encode any kind of message with very small changes of power, and this means we can send any message, any amount of information within 1 second. So let's look at a little bit at a more practical. So those are of course those don't really exist in the real world. So let's look at a real world example. And well, one very general example is a landline telephone line. So an old telephone line had usually a bandwidth of around 3000 Hertz and a signal to noise ratio of around 4000. So this is just the physical, the signal to noise ratio is just what you got because it was constructed in this way. So what is the maximum number of bits that can be transferred per second? Where we can just insert this into Shannon's equation. So we get 3000 times the 2 logarithm of 4000 plus 1 bits per second, which is around 35 kilobits. So if you remember quite in the past, in the beginnings of the internet, the telephone landline was used. The telephone landline was used for data connections, so was used for the internet using such telephone modems. So those dial-up modems were used to transmit data. So from this bound, we know that even in the best circumstances, theoretically, there are only 35 kilobits per second possible. However, maybe if you're old enough, you remember that some later models allowed speeds up to 56 kilobits. And the reason behind this is that they did not really just use the landline, but they used some, so they connected to some, so that they used some tricks to achieve higher bandwidth. So for example, they connected to a local central office where the analog signal was transformed to a digital signal and then sent to a faraway location. So they always just had the telephone, the analog signal for a very short distance, which is how they could make higher speeds. But of course, there were still limitations, which is why this kind of data transfer mechanism got out of fashion. Okay, so again, any questions so far? If not, I will go on. So what we have seen now is that we can trade off. So there's a trade-off between bandwidth and signal power. So either we can increase the bandwidth, or we can increase the power to get more data through to get more data through the system. And well, usually, since both those resources cost money, an engineer wants to use both those resources as efficiently as possible. So we want to use both bandwidth and power efficiently. And when trading one off for the other, there can be some. So there can be some factors to consider. So in some applications, power can be more important than bandwidth, or in other applications, bandwidth can be more important to power. So one has a trade-off to make. So for example, telephone wires have a limited bandwidth, but it's always possible, or it's more easy possible to increase the power than to increase the bandwidth. On the other hand, if we have space vehicles or satellites, then there's a very limited power, so we cannot increase the power, but usually the bandwidth is much easier it's much easier to design a system with a higher bandwidth in this context. And for cell phones, there's actually both is very important. We want to have having a high bandwidth is important to have good internet connections, but also cell phones shouldn't use too much power. So both power and bandwidth is very limited, and we have to be careful using those resources. Okay, let's look at another topic which we will cover in this lecture. So another topic is what is modulation? So modulation is that we change. So modulation means that sometimes it is necessary to change the frequencies of the source before transmission. So sometimes we have to somehow change the signal we transfer before we can transfer it. So reasons for that is, for example, So classical antennas, so in classical radio communication, antenna height is proportional to the wavelength. So if we want to have very high wavelengths, we also have to if we want to have very low frequencies, we have to build very, very high antennas, which is not physically possible. So we have to maybe, to reduce the antenna height, we have to change the rate of frequencies. And also sometimes we want to transfer several signals at once, which is called multiplexing. So sending several signals through the same channel by changing, by having some frequencies assigned to one signal and some other frequencies assigned to another signal. This is one reason why we want to change the range of frequencies. Another reason is there might be hardware limitations of what can even be sent through the channel. And also, well, if there's noise, then there might be more noise at some frequencies and less noise at some others. So we want to change the frequencies to some other frequency range, which will have less noise. And so this process of changing the frequency ranges is called modulation. So modulation is the process of changing parameters of some carrier function according to an input signal. So the carrier function is always assumed to be a sinusoidal of this form. So it has three parameters. It has the amplitude A. So it has the form A times cosine omega t plus phi. So there are three parameters that can be changed. One is the amplitude, which is how high this carrier wave is. The other one is the frequency, which is this omega, which is how many changes per second we have is this omega. So how many of those ups and downs we have in our wave we can change, and also we can move the wave a little bit. We can move the frequencies a little bit, which is the phase, so that we can shift the phase of the input signal. So there are three parameters called amplitude, frequency, and phase, and those are the most important parameters in modulation. In analog modulation, the carrier wave is this waveform, and the carrier is so we get the signal has some other waveform, and so the message here, the message signal is, or sometimes also called baseband signal, is this signal here. And what we do is we let this carrier react to this message signal. So we change the carrier according to this input signal, and then send the changed carrier signal through the channel. And where we can change the three parameters and according to what we change. So if we change so the easiest one is probably amplitude modulation, where we just change the amplitude. So if we go higher here, then we will just let the amplitude. So if the message has some high value here, the amplitude here will be higher. If it has some low value here, the amplitude will get lower. And this is the signal we send. Then we can change the frequency. So if we have a high value here, then we will have a higher frequency here. And there's also phase modulation, which means we change the phase parameter. And we will see all this, all those types and modulations and why they are used and what kind of advantages they have in a later lecture about modulation. And another thing is digital modulation, which means that we have a digital, instead of this analog signal, we have a digital signal which changes the carrier, well, we still have the same types of modulation, but the carrier is now not changed by an analog signal, but by a digital signal, and there are some things we have to care about. So this is also one lecture we will see later. And another central fact is when we send a message, it's often better to not only send the message, but send a little bit more than just the message we want to send. So this is called redundancy, and also similar, sometimes we want to encode the message, so change the message a little bit and do some coding. This is because so randomness is kind of random processes are kind of central in communication, because if there was no randomness, then we would always know what the message. So if the message was perfectly deterministic, then we don't have to transmit it. We already know what the message is if we receive it. So if there's no randomness, there's no need for transmitting any message. And well, this is where probability theory comes in. So probability theory is a measure of uncertainty. And well, one could also say that a less probable message contains more information. And this is the idea behind coding messages. So coding can be used for more efficient transmission by giving more likely combinations shorter codes. And there's also well, we can also use coding to introduce some redundancy. So we can encode some additional, so something like a test bit at the end of the message to detect errors, or if we send even more so if we send, for example, if we send even more information, it's even often possible to not only detect errors but even correct the errors. And this is why coding schemes therefore not just try to encode, make the message shorter, but often also make the message, artificially make the encoded message longer again to introduce some redundancy to make it possible to detect or correct errors. Okay, and one last thing we want to talk about in today's lecture before we will also talk a little bit about history in the end, but one last thing about communication is about this about hard facts about communication is how the channel is actually made. So the transmission media, so the physical path between transmitter and receiver. So there are two types. So it can usually be classified into two types. One is we have a wired channel, which is sometimes also called a guided channel, and a wireless channel or unguided channel. And examples for guided channels, so we will look at those examples a little bit on the next slides. But so examples of guided channels are, well, wires. There are different types of wires. They are called twists. So the important wires that are used in practice are twisted pair wires, coaxial cables, and optical fibers. And well, for wireless communication, so for example, radio waves are used, microwaves are used, and infrared waves are used. Okay, so what are those? So let's look at first look at what kind of cables are used, what kind of media is used for wired communication. So the easiest one is twisted pair cable, which is used for bidirectional communication, which is why it's has. So this is why it has always two cables. So it always has cables for communication in both directions, and those two different wires, those two different copper wires are twisted around each other's, and the twisting is done because it reduces noise. If they are twisted around, because the noise comes from different directions. So if we twist. If the wire is twisted around, if the two wires are twisted around each other, then the idea is that the noise that comes from all directions will approximately be the same for both cables. And often there's not only just two wires, but bounded into larger cables, so some bundled into larger cables to send multiple things at the same time. Twisted pair is mainly used for telephone signals, and well, one disadvantage is that it has a quite low data transmission rate. But it is used for those applications because it's very inexpensive and simple to build, but it has low bandwidth and it's quite sensitive to interference and noise. And well, to deal a little bit with interference and noise, there are two pairs of twisted pair cables. One is unshielded, which is the most easy one. And there's shielded, which means that there's some shielding material used to shield the cable from noise. but this makes the cable, of course, more costly and more difficult to install. And the unshielded one is often used in, for example, in Ethernet and telephone cables, where shielding against noise is not, well, where we don't need, where it's more important to have cheap and easy to install cables than to have shielding. A little bit more complicated cable is the coaxial cable, which looks like this. So maybe you have seen a cable like this when you have satellite TV. This is often used. For TV. This is usually used for cable and satellite TV. So in this cable, the outer and inner conductor are each separated with some insulating material. So we have some material around here, and the outer and inner conductor are shielded. And it has the advantage is that we have a higher bandwidth, which is why it is good for those for television, which needs a higher bandwidth than, for example, telephone, and it's less sensitive to interference. But it has the disadvantage that it has a high attenuation. That means the signal strength is over a long distance. The signal strength gets reduced quickly. So reduction of the signal strength over distance is called attenuation. And this is why often amplifiers or repeaters are needed if we use this kind of cable, or it can be only used for short distance. Another important thing is another important type of wired cable is optical fibers. They consist of a glass or plastic core that transmits light surrounded by transparent cladding material that reflects the light. So they often look like this. They are used mainly for computer networking, especially for long distance communications. So they have several advantages. For example, they have quite high bandwidth. They are not very. They have less attenuation than other types of wires, and they are than other types of cables. And they are kind of immune to interference because light is not. Light is not sensitive to light is insensitive to electromagnetic interference. The disadvantage is that they have very high costs, so they are very expensive to build. They can break easily. They are fragile, and they are very difficult. So they are difficult to install. Well, because they break easily, and it's also difficult to install them. So that's why it's often preferred to have other types of cables if those advantages are not important. Okay, so next we want to discuss some wireless transmission media. So wireless transmission is usually more convenient because we don't need cables. And instead of cables, the waves are propagated through the air. So that means waves go from some transmitter antenna to some receiving antenna, and in this kind of wave propagation, we can distinguish between different forms of wave propagation depending on how they go from the transmitter antenna to the receiving antenna. So some forms of so the easiest form is a direct wave, which just goes directly in a straight line from the transmitter antenna to the receiving antenna. Then there's waves that use reflection. So it can be reflected on the Earth, which is called a reflected wave. It can be reflected on the troposphere. So the troposphere is the lowest layer of Earth's atmosphere, and this is where weather conditions take place. So this often reflects. So some kinds of waves are reflected at the troposphere, and then they can they break and can go to the antenna. So this is tropospheric waves. And there's also waves that go even higher called sky waves that goes out of the troposphere to the ionosphere and then go back, are reflected at the ionosphere, goes through the sky and are reflected back to the antenna. And so sky waves can even be used so they can be reflected several times and can be used for worldwide communication, even by using multi-hop communication, where the wave is reflected and then reflected. So where the wave is reflected at the ionosphere, then reflected at the Earth again, and so on, until it receives the antenna. Okay, let's look at the different kind of waves that are used for wireless communication. So the easiest one is radio waves. The radio waves that are mostly used have frequencies from 3 kilohertz to around 1 gigahertz. They are used for radio and television transmission. They are omnidirectional. That there's one big antenna that sends out the signal in all directions, and we don't have to point the antenna in the direction of the waves. It has the advantage that waves are quite easy to generate, and we can penetrate through the waves. They have very high wavelengths, so that means that because of that, they can penetrate through buildings and other obstacles. And they have also, a disadvantage of them is that they change a lot over distance. So they are very sensitive to interference and so on, and have a high attenuation. The second one is microwaves. They have higher frequencies from 1 gigahertz to 300 gigahertz. They are used for sky waves because they can cut through the ionosphere. So this is why they are used in communication satellites. So they often send out by communication satellites. Different from radio waves, they are unidirectional. That means they don't have a very large wavelength, so they have to be pointed in one direction. So they can be only sent it in one direction. So if you have a satellite dish at home, you always have to you need to adjust it so that it points in the right direction, so that the TV signal can be that you can receive the TV signal, which is also what is meant by line of sight transmission. So you have to have a direct line between the receiver and the transmitter. But they can go through longer distances, can be sent through the sky, and they are usually used for point-to-point communication, for satellite communication. But they have quite high costs for setup and usage, because you need of course, for satellites, you need to produce them, you usually need very large satellite dishes, or very large dishes like this. And the one with the highest frequencies are infrared waves. They have frequencies from 300 gigahertz to 400 terahertz. They have the disadvantages that they cannot penetrate through obstacles at all. So even if you keep your hand in front of a remote control, which is actually the only real application, like short distance remote controls, wireless mouse and keyboards and so on are the only real application for infrared waves in communication. So they can only be used for very short distance and cannot penetrate through opticals, but they have the advantage that they have low cost, and using them does not need any license. So if you want to do radio broadcasting, or if you want to do microwave broadcasting, you need to get the government or some entity has to allow you to use this, to send out waves of this frequency. So, but infrared does not need any government or other license. This is why they are often used for those kind of devices that you have at home, like remote controls and wireless mouse and keyboard. And there's also one large topic of this lecture will also be computer networks. Computer networks are special kinds of networks. So they are an interconnected collection of computers that can exchange information between them. They may be linked through, all those physical things we have seen. So it can be cables, telephone lines, radio waves, satellites, and so on. The most common example of a computer network is, of course, the internet. And computer networks are kind of special because they are usually very large. They are very large communication systems. So it's necessary to have some kind of layered architecture. So the advantage of having such a layered architecture is that we can use a divide and conquer approach. So we can we want to separate, we want to split this large system, this large computer system, into several layers to look at each layer individually, which gives which is the famous divide and conquer approach, which is often used in computer science and engineering. And then it's also, we have some kind of modularity, so we can exchange different layers in such an architecture. So exchange layers without changing others. And we can also independently test different layers of this network. So this is why in large networks, for which computer networks are the prime example, layered architecture becomes very important. And one model of a layered architecture is the OSI model, which stands for Open System Interconnection Model, which is one model for the one model for a computer network. So we will look at this in its own lecture, but today I will just introduce those 7 different layers. So the first layer, so in this model we have 7 different layers. The first one is the physical layer, which is kind of the physical structure and how the channel is made. It's like, for example, a cable or wireless communication. Then there's a data link layer, which handles moving data in and out of the physical layer. There's the network layer, which is responsible for packet forwarding and routing. So this is where, for example, the IP protocol comes in and so on. And there's the transport layer, which is responsible for the end-to-end connections between computers. So this is where TCP and UDP are some keywords of this. There's the session layer. The session layer is responsible for opening, closing, and managing sessions between end-to-end connections. There's the presentation layer, which is responsible for presenting the data in a standardized format, so translating the data from some format to a standardized format like JPEG, MPEG, and so on. And finally, there's the application layer, which is the layer that directly interacts with the application. And so we will see each of these layers in more detail in later lectures. So today is just an introduction of this model. Okay, so the final part of this lecture will just be a short overview over the history of communication. But before that, are there any questions about the content of today's lecture so far? Okay, if not, then I will tell you a little bit about the history of communication. Well, of course, the history of communication can already be said to start in prehistoric times, because there was already communication using smoke signals, drum, etc., and so on. Well, communication in this lecture, as I told you, is kind of modern telecommunication, which means electric communication, and begins with the telegraph. So in the 1840s, there was the invention of the electrical telegraphy, and Morse codes was maybe what we could call the start of modern telecommunication. And then, well, one important theoretical breakthrough was in 1864 when Maxwell gave his famous equations. So what Maxwell's equations do is they provide a description of electromagnetic phenomena, and they link electricity and magnetism. So before that, people usually thought that electricity and magnetism were different concepts, but after Maxwell's equations, people could see, well, one could see a link between those two things, and they led to the discovery of the electromagnetic spectrum, and is therefore kind of the basis of all modern communication. Well, a little bit later, in 1876, Alexander Graham Bell invented the telephone. So, well, there were some other people that worked on different technologies, but he was, so in 1876, it was when he was the first one to file the patent, and so this is why he is commonly known as the inventor of the telephone. And well, a few years later, in 1887, was kind of the start of wireless communication, when wireless telegraphy was, when the first wireless telegraph was built in 1887. And the use of radio waves for that was also used from the start. People started using radio waves from the beginning of the 20th century for communication, but the first public radio broadcast was in 1910, and in 1927 there was the first television device could be bought, I think. Another important theoretical breakthrough was Nyquist's sampling theorem that we have seen on the previous slide. So with all those inventions that have been made in the beginning, in the end of the 19th and the beginning of the 20th century, it became more and more important to also understand the theory behind communication. So apart from Nyquist's sampling theorem in 1928, another important breakthrough was 1948, when Shannon published his groundbreaking paper, which was called The Mathematical Theory of Communication. So this paper here, which marked the beginning of a new field called information theory, and which still is the foundation of today's research in communication and information theory. Because this paper was so important, so the paper was called A Mathematical Theory of Communication. But just 1 year later, the paper was published again as a book, and the title became The Mathematical Theory of Communication, to symbolize that it's not only just some mathematical theories, but the theory of communication. There also have been many practical developments in the first half of the 20th century. So, FM radio transmission was invented in 1933. So FM means frequency modulation. So this is a kind of form of modulation that we will discuss in detail in some of the later lectures. It was invented in 1933, but in the beginning it was not very popular. But later it was discovered that it is much more resistant to noise, and it therefore became the most popular technique for radio transmission. The first electronic computer was invented in 1946, which was the ENIAC, which stands for the Electronic Numerical Integrator and Computer. And in 1962, satellite communication started with launching of the first communication satellite, which is called Telstar 1. It's this one. This here is the ENIAC, the first computer. So in 1969, in the second half of the 20th century, the most important inventions were probably the internet and the mobile phone. The history of the internet starts with the ARPANET. ARPANET stands for Advanced Research Projects Agency Network. And it was first, so the ARPANET is the predecessor of the internet, and it was first established in the Department of Defense of the United States in 1969. And it was quite a complicated network already. It connected different computers at different locations. So this is a schematic map of one early version of the ARPANET, which shows how the computers are connected between each other. So as you can see, the type of connections became more and more complicated, and so it became necessary to invent more sophisticated protocols for communication. The important one is probably TCP/IP, which was installed in the ARPANET in 1982. And finally, in 1985, which kind of is the beginning of the internet, because then the ARPANET was renamed to the internet. And the World Wide Web, which is part of the internet, which is responsible for displaying websites and so on, was invented in 1999. For mobile phones, the history of mobile phones begins in 1937, when the first mobile cellular phone was invented by Motorola. And the first generation of mobile phone networks, today known as the 1G network, was launched in 1979 in Tokyo by NTT Corporation. Well, 1G technology still used analog communication technologies, but all later generations of mobile networks used digital communication. So this is what from the 1990s happened. There were two important trends. The first one is that analog communication was more and more replaced by digital communication. For example, radio and television was analog previously, but nowadays most of this is replaced by digital. And the second trend is sometimes known as wireless revolution. So better and better wireless devices were built. And so the start of this is that for mobile phones, the second generation of mobile networks was launched in 1991. And well, the main difference here is also, again, the switch from analog to digital communication. And this also allowed to transfer not only voice, but also other forms of data, such as short messages through the network. And the third generation was launched in 2001. The third generation allowed higher data transfer rates and made using mobile internet using the internet on cell phones possible. And as that the internet became more and more available also led to Web 2.0 services such as Facebook, which was launched in 2004, which dramatically changed the way that we communicate today. And in 2009, finally 4G, and in 2019, 5G. Well, 5G is currently launched in many countries. So first countries that launched 5G started in 2019. And well, the main differences is that there are even higher bandwidths, which allow, so 4G made video streaming and larger downloads possible, and 5G will allow, will have even much higher data rates and less latency, allowing many applications, such as for the Internet of Things and virtual and augmented reality. And so kind of so to end this lecture, so what is the future of telecommunications? So this area remains an active area of research. So according to one source, in 2020, the global telecom industry had nearly 5.6 billion unique subscribers and 5.6 billion smartphones. So nearly everybody owns a smartphone today. And well, there's 5G technology has been launched, and there will be 6G and so on in some time. And the Internet of Things and smart cities, where everything is connected, has just recently gotten much attention, and this will be built in the future, which also means that there will be more and more data available. It will give rise to augmented reality applications, and there will be lots of machine communication, and also like giving lectures from home and working from home has kind of become the new normal. So this area of communication theory will remain very important in the next couple of years. Okay, so this is the end of the lecture. So thank you very much for listening. Are there any questions so far? Any questions about the content of the lecture, organization, or so on? If not, then today's lecture is over and you're allowed to leave. So see you next week at the same time and place. So the team link will stay the same. The link for team will be the same every week. So yeah, and if there are any other questions, you can also use the Moodle forums and so on. So thank you. Bye.